I'm gonna start talking about radioactivity, right? Okay, now talk about first of all what type of radioactivity radiations we have, take care their proportions. Okay. What is ionization? How to create ions? Take care. Then we learn about gigamolar tube here. Take care. It basically generates electrons here. What is it used for? What does it do? Then we have three types of nuclear emissions. That is alpha, beta, gamma. We talk about these three emissions here, right? The properties and what are their sort of the behavior in magnetic field lines and electric fields, basically electric fields here, right? And then we learn about some particle tracks, some experiments which you basically saw in your past paper recently. Then here, what is decay over here, right? How does alpha particle gets formed? How does the beta particle is produced? How the gamma emission basically takes place? Half life, ठीक है? Small question over here just to see how does it work and where they used some dangers and safety precautions there, right? So it's not so difficult. It's just type of basically particles which are thoroughly discussed over here, right? So we have how many type of radiation over here? Present right now we have basically cosmic rays, right? We have cosmic rays. We have radon gas, which is basically radioactive over here. Uh, some basically if we use granite rocks at our homes to build some let's say some part of our homes, they're radioactive, right? And they are made up of basically they emitted radioactive radon gas, okay, which is again alpha particles, right? And they can harm your body and your sort of surrounding, right? Radioactive radioactive elements, that is potassium, that is available in food and also in your banana, okay. It is radioactive, but not so much slightly, right? If you basically let's say we absorb. If you take a food which contains some potassium in a huge quantity, that might be harmful for you, right? So some are used in medical field. And thinking about gamma rays, they used to kill cancer cells. Okay. They also used in building sort of industrial engineering, where you want to basically find cracks in building. Okay, if you have a default in a building, they emit gamma ray because that can pass through walls, right? It is also produced in power station, right? Let's say we have nuclear power plants. We thought about nuclear fission, right? That is used to produce energy. So again, that is producing radioactive energy, right? That can basically cause a huge uh, sort of drawback, right? Let's say it explodes nuclear bombs, right? They basically carry out fission, right? So this is the proportion over here that what sort of radiation are available right now. What are the proportions that how much are they available? It's a pie chart over here. Shows the proportion here, right? It's a pie chart here. You know, okay, what are pie charts? Basically, they're complete. If you combine all of them together, that makes basically 100% here, right? And you can just figure out okay, how much is it available, basically present in the surroundings. Okay? We have radioactivity in here. That is a huge chunk, right? Radiations are available in cosmic ray, which comes from the surroundings, from the universe, from the space, right? That is again a huge proportion here. Rocks, right? We have uranium rocks, we have granite rocks. Okay. Food, again, it's a huge proportion. We are consuming radioactive food also, right? Medical and again, they're used for doing medical processes like killing cancer cells, so on and so forth. Right? We have radiations in nuclear bombs and nuclear power stations, so on and so forth, right? What is the ionizing effect of radiation over here? Take care. Let's say if a radiation hit an atom, right? Let's say if you're exposed to some radiation, right? You also have atoms inside your body, right? Your body is made up of atoms. So what can it do? Let's say if you're exposed to a radiation, right? So it can basically uh, displace an electron here, right? What happens? Let's say if a ray is hitting your body, right, and it might basically cause your cells that are made of atoms to become abnormal, right? So if the cells become abnormal, it is cancer, right? So what is happening over here? It basically ionizes your body here, right? So you can see the electron was present here after radiation basically passed through an atom here. So it basically caused the ionization of the atom here. That is, it's caused the electron to split, right? Now you have a positive ion, okay? Let's say it was hydrogen, right? A positive ion here. So again, this is creating abnormality in your cells, right? So this is the effect of radiation, right? So what are they doing over here? You have a charged electroscope here, right? We discharge this when the light is matched or a radium source is basically brought near the cap. Okay, so you have a charged electroscope here. So if you bring a light match, okay, we basically do what? It will basically discharge an electron, right? It basically ionizes itself over here, right? So if I basically bring a radium source here, again, it basically does this process here, right? It basically ionizes an atom, right? So I hope it makes sense. Okay. So what is happening here? They are saying here you have a charged electroscope which basically emits an electron. Okay. That is, it had an atom, neutral atom. When you brought in a lighted match or a radon, that is a radioactive source. So it basically carries out this process here that is called ionization. Right. Again, this is the effect of getting exposed to a radium source here. Right. That's explained using experiment here. Then we have Geiger Muller tube here. So let's see ke why is it used? Why do we have this? What is it used for? Okay. So it basically generates electrons here, right? It basically generates an electron, sort of a ray of electron, right? Let's see how does it work. So when a radiation enters a Geiger Muller tube, right? It basically detects it, right? Okay. So how does it happens? So it basically passes through the thin mica sheet, right? And if the radiation is very penetrating, it can basically pass through the wall. Okay, creates argon gas, ions, and electrons over here, right? So these are, I said, these are basically passed on towards the electrodes, which are more basically which causes more ionization. Okay, and the argon starts to lose electrons when the gamma or the any radiation hitting the gigamolecule. Okay, basically starts counting the number of electrons which are hitting the mica sheet, right? It basically is a sort of the radiation counter here, right? If you want to count that how many atoms are losing electrons, that is, if you hit an atom with a, let's say, a radioactive source, it is going to ionize it, right? And what is ionization? Basically loses the electron. When the electron is lost, it hits the mica sheet. The counter basically adds a one to it. Okay, we have now the first radiation received over here. Okay. The first atom is basically now ionized here. That is basically we have some radioactive source in the surrounding state. So on reaching the electrodes, the ion produces a small current pulse, which is amplified and fed either to a scalar or a rate meter. We have a counter or a selective software, which is basically counting how many electrons are hitting basically on the mica sheet here. Right? A scalar counter basically counts the pulses and shows the total amount in a certain time. But how many, let's say, strikes were there on the sheet in a certain amount of time, right? So this basically gives you counts per second or minute, right? Okay, how many counts? That is how many strikes were there per minute or per second on the screen. Okay, and that is called the count rate. Okay, it is important in radioactivity, right? This term is important in radioactivity. Okay, I hope it makes sense. Okay, so what is happening over here? So we have a thin mica sheet over here. Okay, let's say we have some alpha particle here, right? And they're stacking the mica sheet over here. So what does it do? We have argon gas inside this. Okay, so this alpha particle can pass through the mica sheet, right? So what happens? The argon elements, basically the atoms are ionized, right? And so basically, how are they ionized? They basically lose the electron here, right? So as the electron is lost over here, so you can see that electron are going to hit the anode wire, right? Anode is basically positive, cathode is negative. Okay, and the argon anions, because argon has lost one electron. Okay, let me just fix my spelling here. Argon lost one electron, it had basically became positive here. So it goes to a cathode, basically metal cylinder here. Okay, so it completes the path and a current flows. Okay, a current basically flows over here. Let's say the first electron basically strike the anode. Okay. So it basically, it has a variable that is called count rate. It makes it to basically, let's say it counts, basically it is the counts. What is happening in my spelling? It counts basically what? It counts per second, right? So let's say the count was zero. After the electron basically strike the anode, the current will flow, electron will flow, okay, obviously, and the count will become one, right? And so on and so forth in a certain amount of time. That is how the gigamolarity works over here. Basically, the radioactive, it is basically the radiation counter over here, right? If we have very high amount of counts per second, that means that the source which is producing the radiation is very strong, right? Okay. So now we have basically three parameters which basically you should know about a radiation. That is, what is their penetrating power, that can it pass through walls, can it pass through glass, can it pass through paper, can it pass through a human body, okay? And its ionizing ability, that how strongly it can basically make an atom lose electron, right? If it is very high ionizing, that means it is very harmful for the human body, right? Or it can cause abnormality in your cells, right? And the behavior of radiation in magnetic and electric field over here. So we need to basically know these four properties of an radiation, and that's how we can define three type of radiation. So we learned three type of radiations over here. That is alpha, beta, and gamma, right? Alpha का symbol हमारे पास होता है ये. Basically, my PowerPoint change the variable. Alpha is this, okay, and then the symbol for beta is this, and the symbol for gamma is this, right? ठीक है जी. I hope it makes sense. So, what is the procedure? So, how is the experiment going to be? So, we will have a source, right? We will have a source here which is producing any one type of the source. Okay. We'll have a small hole here which is going to basically pass a ray of that particular radiation here. And then we have the Geiger molar tube here. Okay. Which we just learned. Okay. It is going to count, okay, how many counts are here, which is basically counting the strength of the source here, कि how strong are the radiation produced here. And this is the rate meter which basically counts, gives you counts per second or minute, right? ठीक है. Then this is the setup over here. So I hope it is clear over here. ठीक है. You can pause it and just see what is happening here. अच्छा जी. So we have three experiment setups here which we can do to differentiate alpha, beta, gamma. So we have three sort of materials here. We have a sheet of thick paper, right? We have a sheet of aluminum which is 2 millimeter thick, okay? And then we have a sheet of lead which is 2 centimeter thick, right? So we're gonna have, let's say, three sources here. We're gonna have three sources here. One is going to be alpha, one is going to be beta, and one is going to be gamma here, right? So we're gonna place first of all paper, and then a 2 millimeter thick lead, and then a 2 centimeter thick, sorry, aluminum, and then 2 centimeter thick lead here, right? This is going to be paper, and this is going to be lead, and this is going to be, sorry, not lead. This is lead here, and that is aluminum, and this is going to be aluminum, right? You will see can alpha particles pass through paper, or are they blocked? Can they pass through aluminum, or are they blocked? Can they pass through lead, or are they blocked, right? So this basically experiment will give us the penetrating power, right? So if we can reduce using this experiment, we can just identify, okay, this source is producing let's say beta radiation, this is producing alpha radiation, this is producing gamma radiation over here, right? Yeah. So let's start. Okay, let's start. Okay, Ji, so let's continue. Let's go to the first type, that is alpha particles here. So let me fix this. This is basically alpha particle, right? So what is the alpha particle property here? That is, if you have an alpha particle source, right, and if they're basically hitting, let's say, going in this particular line, if you basically place a sheet of paper here, okay, so this is enough to block alpha particles, right? So this will block alpha particles. It basically blocks them. Okay. So these are stored by a thick sheet of paper and have a range of air in only few centimeters. That is if you have a alpha source. If you are far away from the alpha source, say that is your same rate. So if you're pretty close to the alpha particles, that means that then you can be exposed to alpha particles. Right? But if you have a sheet of paper, a thick sheet of paper placed in between, that is going to block all of the radiation, almost a major chunk of the radiation, right? Uh, they cause intense ionization of in a gas, okay, due to frequent collisions with the gas molecules here, right? So what are the properties here? Their penetrating power is pretty small. Their penetrating strength is weak. Why? Because their ionization strength, that is, how strongly it basically causes an atom to basically lose electrons. Right? So it has very high strong basically ionization strength. That is why it cannot basically move further away because it is causing the atoms nearby to basically ionize and it cannot travel further away. Right? Then since they are basically positive particles, okay, these are also called positive particles. These are positively charged, right? And the helium is basically an alpha particle, right? Helium is basically an alpha particle, right? So these are positively charged here, right? So again, since they are positively charged, they would be basically deflected. They would be deflected in a magnetic and electric field. Okay, so these are the three properties of the alpha particles here, right? So they are deflected by electric and strong magnetic fields, right? Uh, okay, by a huge amount. That is why it suggests helium atoms minus two electrons ions basically with a double positive charge over here, right? So what is a helium atom? It basically is it is 4 2 here. So it has basically two protons, two electrons, okay, and two neutrons here in a neutral atom, right? When it becomes ionized, okay. Let's say it has lost two electrons. Now it has basically two proton number, it has zero electrons, it has two neutrons. So it is overall positive two, right? It is heavily positive particle here. Okay. Then we have beta particles. They can pass through paper, right? They can pass through paper. They can pass through paper easily, right? If you want to stop them, you want to stop them using a basically a 2 millimeter basically aluminum sheet, right? So these are stopped by a few millimeters of aluminum and have a range in air of several meters, right? So they can go further as compared to alpha particles, right? So why they can go further because they have very small or weak ionizing power. That is, they cannot interact with the atoms strong enough as compared to alpha particles. Okay. These are deflected by electric fields because what are beta particles? Beta particles are just electrons, right? These are electrons, so they have basically very small mass and they have very high speed. That is why they can go for further distance as compared to alpha particles. And since they are negatively charged they are electrons, so they should be negatively charged, right? So they can do what? They can basically, again, if you basically pass beta particles through a magnetic field or an electric field, they're going to experience a force, right? They are deflected by magnetic field lines as well as electric fields over here, right? So beta particles are streams of high energy electrons over here, right? So you can see that if you have a magnet here, you can see you have a magnet here. If you have a beta particle source, right? So this magnet causes the beta particle to deviate. Okay, they change the direction here because they are affected by the magnetic field lines. Okay, and this is the counter over here is counting the strength of uh, the radiation of it. Okay, so I hope it makes sense. This is not so difficult. Just the basics. Okay, this gets intensive when you're A2 because you will go further into the depth. This is the experiment in zoomed in over here. I hope it makes sense. We have a source. We have a strontium source which basically produces beta particles, right? And we have basically a thin sort of a outlet to allow the streams of electrons or beta particles to go in a line, right? And then we have a magnet over here which basically does what? We have magnetic field lines in this direction, right? And the beta particle goes through magnetic field lines. You can use your Fleming's left hand rule. Okay, so beta is just an electron, right? So what does the thumb show? We have done this. I guess we have done this in motor effect, right? So the thumb shows the sort of the fourth motion here. The first finger shows the magnetic field direction here. The second finger shows the current here. So the magnetic field goes from north to south. So it is like this. Okay. And the current is basically going where the current is basically in this direction. Right? Let me fix it over here. So it has north to south. And then we have electron in this direction here. Okay. So yeah, the force is basically outwards. So basically the electron is getting repelled outside, right? So it is basically bending in this direction, right? It's bending in this direction. It is bending in this direction. Right? Okay. Okay, pause it. You pause the video again, go back, pause when I was basically making my right hand move. Okay. And it will make sense. Okay. Then we have gamma, gamma emission, right? So what are gamma emissions? These are basically high speed. These are basically high speed electromagnetic waves. ठीक है? It has no charge by the way. That as it is neutral, right? So what are the properties of gamma emission? That is, it is the most penetrating. That is, it can easily pass through paper, it can easily pass through aluminum, thick sheet of aluminum. But if you want to stop it, you want to use a 2 centimeter thick lead, right? This can basically stop the gamma emissions by a certain proportion here, that is around 80, 89, 92%. Right? The small amount still passes through it. They basically can penetrate the most because they have the least ionizing strength because they are neutral, right? They will not affect any atoms nearby. Okay. And they basically have the third property, that is they are not affected. They are not affected by electric or magnetic fields because they are neutral, right? They need to be basically deflected in an electric or magnetic field. It needs a certain charge, either positive or negative, right? It is neutral, so it goes straight, pass through, goes straight through the fields, right? So yeah, this is the property. They are the most penetrating. They are stopped by only by many centimeters of lead. Okay. They ionize the gas even less than beta particles. They are not deflected by electric and magnetic field lines. They give interference and deflection effects, and they are basically electromagnetic radiation traveling at very high speed. That is the speed of light. And what is the speed of light? You know what is the speed of light? That is 3 exponent 8 meter per second. Right? That is the speed of light. Okay. So yeah, these are the three type of emissions which you have learned, and now you will see the effect of these three basically radiations under magnetic field and the electric field line. So these are the three radiations under magnetic field line. The cross shows that the field is basically into the page. That is, you have a north pole at the front of the screen and south pole inside the screen, right? So it's going in. Okay, that is into the page. So if you have a alpha particle, right, you can use a right hand rule, left hand rule basically. हमने किया था. So you have a magnetic field line that is going into the page, that is inside, right? And you have basically the positive flow. Okay, we basically fix this finger towards conventional current flow, right? What is conventional current? It is basically direction of positive charges, right? So positive charges are moving in this direction. ठीक है जहाँ पे alpha particle move कर रहे हैं. So you have a force at the top, right? So that is why they're deflecting here. The alpha particles are deflecting here, right? So gamma particles are neutral. So basically alpha particles are positive. Gamma particles are neutral, zero charge, so they go straight. What about beta particle? Same thing. The magnetic field is basically into the page. So we take the positive flow. Okay. So if electron are moving in this direction, okay, that is the direction of the beta particle entering. So positive would be opposite, right? So you have a force at the bottom. That is why the beta particle are going down. Okay. Force on beta and force on alpha, right? So this is how they behave in the magnetic field over here, right? You can see that beta particles का जो हमारे पास deflection है, that is pretty heavy, right? Because alpha particle is a helium particle here, right? Okay, that has lost two protons, two electrons basically. Beta particle is just one electron, right? So electron has a very small mass as compared to alpha particle, so it deflects the most. Okay. What about electric field? Pretty simple. You have positive plate at the top, negative at the bottom here. Gamma ray goes straight because it has zero charge here. Beta particle is negative, it should go towards positive. Okay, so it goes up. Okay, this is negatively charged. And the alpha particle is basically going towards what? Is going towards is going towards basically the negative charge here. And why is alpha particle deflected the most here? Because it has basically charge of +2, right? And beta particle has a charge of -1, right? So if you have a strong charge, it means it has a strong force of attraction. That means that an electric field is going to basically pull more strongly. This was opposite over here because it is not dependent upon the charge strength here. Okay, it only in magnetic field line in magnetic field it only depends upon the masses here, right? That the beta particle is just one electron. It is basically 1/1840 times the mass of proton. Right? So we have alpha particle which contains two proton and two neutron. It's pretty heavy, right? So it bends, but to a smaller extent. Okay. Then we have some experiments over here which were done to basically observe them in a nuclear chamber here, just to basically observe the pattern. How does it look like in experimental way? So we have the experiment over here. The paths of particles of radiation were first shown up by the ionization they produce. Okay, that is called cloud chambers. So we have cloud chambers which basically have some elements here. So we basically, let's say, pass alpha particle or beta particle or gamma particle through a hole into the chamber. So when the particles ionizes, it will basically produce some pattern there, right? So when air containing vapor alcohol is cooled enough, saturation occurs. That is basically the traces जहाँ से पार्टिकल गुजरे थे वो लाइट होंगे. यहाँ पे कुछ बेसिकली पार्टिकल्स condense हुए हैं यहाँ पे basically there would be a thick region over there. So you will have some certain pattern from it. So if ionizing radiation passes through air, further cooling process causes the saturated vapor to condense to the ion created. The resulting white line of a tiny liquid drop shows up as a track when it is basically glown, right? When it glows. You can see the alpha particle are like this, right? It is pretty strong. It has a strong basically ionizing strength over here. So it basically ionizes the particles pretty strongly. You can see the particle traces. ठीक है जो उसने ionized की. It's pretty huge and it is uniform, right? As compared to beta particle. So they have very weak strength of ionizing. That is, the ionize is very small as compared to the alpha particle here, right? Okay, so the patterns are basically where the particles were basically ionized, right? The remaining regions are the ones where the atoms are basically stationary. Okay, and then now we have radioactive decay, right? What is radioactive decay? First of all, they might be questioning in your head, okay, sir, how are they produced? How do we produce alpha, beta, gamma radiation? So they are produced after some process called decay. That is radioactive decay, right? So radioactive decay by definition is the emission of an alpha or a beta, okay, can also add up, or a gamma, okay, gamma particle, okay, from an unstable nucleus here, right? So during an alpha or a beta decay, the nucleus changes to that of a different element, which may be itself be unstable. After a series of stable, after a series of decay, then you might have a stable element produced. Okay, so what is meant by stability here? Okay, so if you have a neutron number greater than 82, okay, that means that particular element is unstable. Okay, if you have neutron that are less than 82, okay, so that elements are called stable elements. Okay, so this is how it works over here, right? So how does alpha decay works? Okay, alpha decay is just the production of helium particle, right? So you can see this particular reaction here. So we have radon that is 22688. It produces basically what? Alpha particle is a helium nucleus here having two protons and two neutrons. When atom decays by emission of alpha particle, its nucleon number decreases by 4 and its proton number decreases by 2. Right? When radium basically क्या नाम है, radium decays, it produces radon here, okay, plus our alpha particle. Right? So how should you learn this? How should you learn? How do we learn any alpha decay over here? So let's say if we have element X that has basically A here, Z here. If it decays to produce alpha particle, right? So you will have a daughter element that will have less, basically a mass number which is reduced by 4 and a proton number that is reduced by 2 because that is adjusted in the helium. Okay, this basically particle is basically called alpha particle here, right? So if you want to make sure okay, the sides are balanced, that is the law of conservation of mass is basically getting satisfied here. Law of conservation of mass. So you can check the following things. You can check the mass nuclear number and you can check the proton number. That is, both should come out to be same on the left hand side and the right hand side, right? So let's check for A here. Okay. Let's check for not A. Let me just write it down. Let's check for the nuclear number. Okay, so it's going to be A equals to right hand side, that is A minus 4 plus 4, right? So this cancels out. Therefore, we have A equals to A. That is, we have same number of nucleons on the left hand side and the right hand side, right? So similarly, you can check. I can check for the proton number. So it's going to be Z equals to Z minus 2 plus 2. This cancels out. So again, you have Z is same as Z. That is, proton number is conserved here. That is the law of conservation of mass is getting satisfied here, right? So this is basically an alpha decay. Okay, you can check it out over here. It happens same over here, right? So you had 226 of element radium. It basically produces alpha particle, which is basically 4 2, right? So the nucleon number of the total element is reduced by 4. That is 226 minus 4 is triple two. Okay, and if you see the proton number, okay, it was 88 here. Then on the right hand side you have 86 plus 2, right? So 2 is for the helium here, 86 for the radon here, right? So that is how alpha decay works, right? And then you have beta decay. How does beta decay basically take place? Okay, this is beta negative decay. Okay, a neutron changes to a proton and an electron, right? Okay, so let's see how does it make sense? A neutron is what? It has mass number 1, it has 0. This is the representation of neutron here, right? So if you basically check, okay, is it getting satisfied here? Okay, is it correct or not? So let's see what do we have here. So it converts into a proton and an electron here, right? So proton has basically what? It has a mass number of 1. It has a charge of plus 1, right? And the electron has a basically mass of 0 and a charge of negative 1. Right? So let's see if it is conserved or not, right? Let's see if it is conserved or not. Okay. So if you check, the nuclear number is going to be 1 equals to 1 plus 0. So it's coming out to be 1 equals to 1. That is, your mass number is conserved. That is, this particular thing is getting satisfied here. So this electron is basically your beta particle. Is a beta particle. Okay. Let's check your, this was your A. Let's check your proton number here. Is it getting same here? So neutron has 0 protons, obviously. Okay. So it is 0 equals to plus 1 minus 1. So therefore, this is coming out to be same. That is, the proton number are also coming out to be same in this particular reaction. Okay. So this is the equation for your beta decay here, right? So let's see how does carbon 14 produces a beta decay here, right? So you have, sorry, my PowerPoint is crashing. Let's wait for a few seconds. Yeah. Let's see how does it convert to nitrogen. So we have carbon 14 and 6, right? Okay. So what happens? It converts into what? Nitrogen 14, 7 plus a beta particle, which is basically an electron or charge, -1 and 0, right? So what happened over here? You can see that the mass number is same, right? The mass number is same. If you check the mass number, let's see how is it getting true. So let's write down an equation for beta decay. Let's write down an equation for beta decay. Let's say if you have element XAZ, if you have a beta decay, it will produce a rotor element of basically same mass number and a Z plus 1 plus a beta particle that is -1 and 0. Right? So this is your beta decay standard equation here, right? So let's check your A here. Is it getting satisfied here? So it's 14 equals to 14 plus 0. Therefore, you have balanced left hand side and right hand side here. Let's see if you have balanced proton number or not. So you have 6 equals to 7 plus minus 1, right? So it's coming out to be 6 is same as 6 here, right? The proton number also same here, right? So therefore, this equation is correct. You get it? This is beta decay. What is gamma decay? Okay, so basically in every decay, that is alpha or beta, you have basically gamma addition produced, right? So this is a gamma particle here. Okay, this is a gamma ray. They are produced in every reaction. Okay, they are basically high speed electromagnetic waves. Okay, so they are produced in all of the decay processes. Right? So if you have this, you will have a plus gamma ray here. Okay, so these are just after emitting alpha or beta particles, some nuclei are left in excited state. So rearrangement of the protons and neutrons occurs and a burst of gamma emission is released. Right. So in every sort of decay, you have gamma emission produced. Right. So they are just high speed electromagnetic waves. Okay. I hope that makes sense. You can take a pause, take a break, have a cup of chai, coffee. Okay. Then continue. Right. Now it is double work for me because I have to record twice now. Then you have half-life. Now we're starting about radioactive decay. Decay half-life, their activity graph. Decay will do this on your own. This is examples. This is a solved example over here. Some uses ranges and safety precautions. So what is half-life basically? We have talked about this in the past several sessions. So let's say you have an element here. Okay. This is, let's say, contains mass m, right? So half-life is basically the time. Okay. It has a symbol of T subscript half. So it is the time taken for the mass to reduce by half. You can see a mass goes to m upon 2, it has become half, right? So the half-life of the particular isotope is the time taken for the half of the nuclei of the isotope in a given sample to decay. Decay means decay by producing radiation, right? So radiation in the we have, let's say, alpha particle produced, that is a helium atom, right? So it is losing mass continuously, right? So the time it takes to reach the half of its value is called the half-life. right? Usually, if you recall, okay, we are getting dinosaur okay, samples, and they used to live millions of years ago, right? So we have found some small chunks of the bones, right? The rest of it has decayed already. Okay. So we can also trace back to find out okay, this dinosaur used to live around this particular year of time. Okay. So this is how we can, this is important also and harmful also, right? So the entire atmosphere which you're looking at now is idiot, right? So it is difficult to know when a substance has lost all of its radioactivity, but the time for the activity to fall to its half value is easy to find, right? You can basically use a gigamolar tube just to basically keep the count rate. And as soon as the count rate goes to half, that is your half-life, right? So this is the definition we should learn. So half-life is the time taken for the half of the nuclei to basically decay. And this is how basically you plot graphs, right? So what is activity? Basically, activity is counts per seconds. Okay. So if you recall your gigamolar tube, it is counting activity. How basically active is the source, right? It counts basically counts per second, right? So initially when time is zero, okay. So this is the initial activity of the source which you plot to test, right? So this is the initial activity A naught, which is 80 here, right? So you can also count this as a strength also, right? It has less initial amount of mass that is 80, right? So now after some time, the mass basically the activity goes to 40, right? That is the number of counts now that are getting received is now half. That means that it is losing its strength, right? That is it is also reducing its mass. Okay. So now the time taken to go from A0 to A1 is called the half-life. Okay, and this is the decay curve over here, which you should know about it. This is the decay curve here. Okay. So now they are also taking some samples here. They count some values here in minutes. So initially it was 80, right? After 10 minutes, it became 40. After 20, it became 20. After 30, it became 10 here. So what is the half-life here? Okay. So this is basically plus 10 minutes. This is plus 10 minutes. This is plus 10 minutes. You can see it goes from 80 to half, 40. And then 40 again to its half value, 20. Then again to a half. So the half-life of this particular substance that is used in the experiment is 10 minutes. Okay. This is half-life basically. So you should basically do this as a homework assignment now. It's a solved example. So just pause the video and just see the slide. Okay, how is it happening, right? This will have you in your exam. So we are also solving questions in the past paper session, so it will basically not be difficult. Again, they're helpful also, right? So this is basically gamma. This is gamma, right? So gamma radiation are used to sterilize medical instruments by killing bacteria. It is also used to irradiate certain foods, killing bacteria to preserve food or lumber, right? Then we have beta emitters. They are suitable for monitoring the thickness of thin sheets. Okay? And gamma can be used to basically find cracks or let's say observe thicker materials because it has more penetrating power, right? And then we can use gamma rays is used in killing cancer cells. Okay? Where basically we place high energy beams of gamma radiation, okay, or not on a tumor that is basically a cancerous cell, and it can basically kill those particular cells if you expose a certain amount of radiation. If you are overexposed to a gamma radiation, again it is harmful. Right? So the beams are rotated around the body to minimize the damage to surrounding tissue. Right? Then we have some dangers over here. That is the ionizing effect produced by nuclear radiation causes damage to cells, tissues that can basically create abnormality and basically create cancer cells. Right? Okay, if we have, let's say, excess cells getting produced, that is again abnormality. If you're getting decrease in your blood cells, right, that is again abnormality. Right? That is a cancer. Right? So this damage may cause cell death and also induce cancers over here. Okay, what are the danger of alpha particle? It is small, right? Because it has very small penetrating power, but again, it has very highest ionizing strength over here, right? So you can call radiation burns if you're overexposed to alpha particles. It can be burn your skin, right? Okay. No, not this. Alpha particle cannot enter your body because it will be blocked by your skin over here, right? But again, if this source goes inside your body, That is a harmful threat. But beta and gamma can basically penetrate your body. So you can you can burn your cells, so on the skin, right? So on and so forth. Right? Even cancer. Large exposure, if you recall, Marie Curie, okay, she died because of this, right? She is a scientist who was the only female person to basically get a Nobel Prize. She was overexposed to gamma particles because she kept a radioactive element in her pocket. That was uranium. She was basically working on uranium. Okay. It was not discovered at the time, right? So she died because of getting overexposed to gamma rays. Okay. Even her lab, the where she used to work, is currently basically radioactive. Okay. If you watch videos on YouTube, give you a highlight of the entire workplace. Again, how can you basically protect yourself from the exposure? Again, the exposure time that you expose to the particle should be very small as possible, right? You should have a distance between the source and the person, right? Because so that it cannot reach your body and go inside your body and cause harm, right? You should use shieldings. Let's say if you want to block gamma ray, you should have a shield of lead, right? If you want to block beta, if you're working with beta particle, you have a sheet of aluminum, right? We should not basically let the ray pass through the sheet and enter your body, right? So that is the entire radioactivity, that is nuclear physics summed up. I hope it makes sense. It's not so difficult. It's just basic terms here. Okay. You have only one formula, that is not formula, just the concept of half-life over here. Baki, the rest is just theory, right? Properties. And this basically ends the chapter. I believe you have you're practicing right now, and I should be seeing for you on WhatsApp group. So till then, Allah Hafiz and